In this video we're going to continue using logarithms to find suitable models from collections of experimental data. Real-life bivariate data does not follow mathematical rules exactly. There'll be some degree of error in the figures that we observe. So if we're attempting to create a mathematical model for real-life data, it's important to start with a reasonable amount of data and then to use all the data to create the model. A reasonable model can then be used safely to make predictions about new data values that lie within the range of values considered. Using the model for data values which lie well outside the range of values of the data should be treated with the utmost suspicion. Given a set of bivariate data, it's worth starting by obtaining a scatter diagram and looking to see whether the data seems to be a linear rule, that is a rule of the form y equals mx plus c, or an exponential growth or decay rule, or a power law. So it's important that we should recognize each of these different types of graph. Now a straight line graph is fairly obvious. In the previous videos we've looked at exponential growth and decay rules. So an exponential growth curve looks something like this. It's growing rapidly. It's got a formula of the form y equals ae to the kx, where k is positive, or we could write the formula in the form y equals ab to the power x, where b is greater than 1. An exponential decay curve has a similar formula to the previous one, but clearly decays rather than grows, and it's got formulae y equals ae to the minus kx, where k is positive, or y equals ab to the power x, where b lies between 0 and 1. So those are the typical exponential growth and exponential decay curves. The power laws are if we've got a curve of the form y equals kx to the n, where k is positive and n is bigger than 1, that grows quickly from the origin. If we've got a power law of the form y equals kx to the n, where k is positive and n lies between 0 and 1, then it passes through the origin and grows, but nowhere near as quickly as if n was bigger than 1. And if we have a power law with a negative value of n, then the line x equals 0 is going to be an asymptote to our curve, and also the line y equals 0 is going to be an asymptote to our curve. So in other words, as x tends to 0, y is going to tend to infinity, and as x tends to infinity, y tends to 0. James has collected some data showing how the length, L meters, of a simple pendulum affects the period for the pendulum, which is the time that the pendulum takes to go from one extreme position to the other extreme position and return back to the original extreme position. The times for different lengths are shown in the table, and what we want to see is whether we can produce a mathematical model relating the time for one period of the pendulum to the length of the pendulum. It's a good idea to start with a scatter diagram for the data. So there's the scatter diagram for the data as it stands. If we had a pendulum of no length, then we would expect there to be no periodic time. It won't take any time at all to go from one extreme position to the other. So we can add one more point perhaps to the data. And that makes it look as if we've got a set of data which is a power law of the form t equals k times L to the power n, where in this case n is going to be some value between 0 and 1. If we have got a power law, we've got a relationship of the form T equals KL to the N. Now we've got to try and find the value of K, we've got to try and find the value of N. At the moment they're all muddled up in a single term. But if we take logarithms, we can separate them nicely. So we're going to take logarithms of each side of the equation. And again, I'm going to take natural logarithms. So I've got the natural logarithm of t will equal the natural logarithm of k times L to the n. Now we've got our four basic laws of logarithms. The right hand side is the logarithm of k times by L to the n. Using rule 2, I can say the natural logarithm of k times L to the n is going to be the same thing as the natural logarithm of k plus the natural logarithm of L to the n. So I've now got natural logarithm of t equals the natural logarithm of k plus the natural logarithm of L to the n. Now, using rule 4, I know that the natural logarithm of L to the power n is the same thing as n times by the natural logarithm of L. So we can now write the natural logarithm of t is equal to the natural logarithm of k plus n times the natural logarithm of L. If I now substitute y for the natural logarithm of t and x for the natural logarithm of L, then I've got the relationship y equals n times x plus the natural logarithm of k. And that tells me that if I draw a graph of y against x, I should get a straight line of gradient n and y-intercept the natural logarithm of k. If I take the values that James has provided me and then add the values of x, which is the natural logarithm of L, and y, which is the natural logarithm of t, if I plot the values of y against x, I'm expecting to see a straight line graph, and the gradient of that straight line graph will be n, and the y-intercept will be ln k. Now we can see indeed that the data points that I've got for x and y do lie very, very close to a straight line. If we put the straight line in by best fit, or indeed by using the calculator to calculate a regression line for the points, then we obtain a line very close to the one that I've drawn there. We can see that the y-intercept is just a little bit below 0.7. It's something like 0.69. And if the y-intercept, remember, gives us the value of the natural logarithm of k, so we've got the natural logarithm of k, it's 0.69, so we've got k is e to the 0.69, which is 1.994. The value of n is the gradient of our best fit line. So looking at the y-intercept and then the point where we've got x is 1 and y is 1.2 almost exactly, we can say that we've got there the gradient is the y-step divided by the x-step. The y-step's 1.2, take away 0.69, which gives me 0.51. The x-step is 1. So the gradient of the best fit line is 0.51 divided by 1, which gives me 0.51. The best fit line is telling me that the value of n I have got is 0.51, the value of k I have got is 1.994. So the analysis that we've done on James's results suggests that an appropriate model linking t and L is the rule t equals 1.994 times by L to the power 0.51. And if we return to the original scatter diagram and superimpose the curve t equals 1.994 L to the 0.51, we can see that it is indeed a good fit to James's experimental data. That concludes the video on finding suitable models from data.